Ladies and gentlemen, welcome back to our lesson videos. We're going to talk about section 5-8, solving radical equations and inequalities. And always we're going to start with a warm-up. So you are going to turn the lesson video off and then turn it back on when you are ready to check your answers. With the knowledge that you have about radicals from Algebra 1, as well as the work that we did in the last section with rational exponents, you shouldn't have had much trouble with these. But if you do have any questions on them, please write your question down on a Post-it, put it in your notes, and let's talk about it in class. Taking a look at our objective for this section, solve radical equations and inequalities, and for vocabulary, radical equation and radical inequality. I know it's pretty self-explanatory to see what they are. A radical equation is an equation that has a variable in the radical or under the radical symbol in the radicand, and likewise with a radical inequality. An inequality would be solved similarly to an equation, but we'll see that there's a little bit of variation on it. We need to make sure that we are working with real numbers and not imaginary numbers, and that's going to put a constraint or a restriction on our domains. Okay, a radical equation is an equation that has a variable underneath the radical symbol or in the radicand. And just as previously, we sometimes took the square root of both sides or we squared both sides, we're going to be doing that in order to solve radical equations. So we're going to be not only squaring both sides, but raising both sides to a power so that we can get rid of the radical symbols. And that's basically our strategy for solving. So make sure that you have the solving radical equations steps written down in your notes. Number one, isolate the radical. That means that the root symbol is going to be on its own on one side of the equation, on one side of the equal sign, so that when we raise it to a power, we can get rid of the radical symbol. Now, the way we raise to a power on the other side kind of depends on what we've got, but we know that whatever we do to one side, we have to do to the other side, and that's what's going to help us solve. So you can see the example on the screen. We have the cube root of x minus 2. We move the 2 over to the other side so that we've isolated the radical. Because it's a cube root, we're going to raise both sides to the third power, and that will mean the cube root and the cube will cancel each other out. We're going to be left with just x on the left-hand side. When we cube the right-hand side, we have 2 cubed is equal to 8. That solves our radical equation. Okay, and just a reminder, when you don't see the index, that means that the index is 2. So you're finding a square root. Okay, knowing what we now know about how to solve, the very first thing that we need to do to solve this equation is isolate the radical. That means the 5 goes over to the other side. And then we have the square root of x plus 1 is equal to 11. Then, just as we said, we need to get rid of the radical symbol, so we're going to square both sides. And once we do that, we have on the left-hand side just x plus 1. On the right-hand side, we have 11 squared, which is 121. And then the last thing that we need to do is just move that 1 over to the other side. So we have solved for x. When we check, we plug back in, and we can see that we got the correct number that we should have gotten. So our equation is in balance, it's equal, and that means that x equals 120 is the correct solution. In question 1b, we have a similar situation where we have a radical on the left and we have a constant on the right. It is a radical equation because we have the variable underneath the radical symbol. And so the first step that we need to do is to isolate our radical, and that means we're going to divide both sides by 7. Then, once we've got the radical symbol isolated on the left, we're going to raise both sides to the same power. In this case, we've got a cube root, so we're going to raise both sides to the third power, and that's going to leave on the left just 5x minus 7. On the right-hand side, you can see that we've got 1,728. 7 moves over to the other side, and then we divide both sides by 5. Once we plug our solution back in to make sure that it works, we can see that we do end up with a balanced equation, a true equation. So we know that x equals 347 is a correct solution. Let's take a look at example 2. This one is slightly more complex than example 1 because we have radicals on both sides of the equation. However, we are going to have a similar strategy where we're going to square both sides. And remember, when we square the right-hand side, we square the 3 and square the radical. Those two numbers are multiplied to each other. So that's how we square to the product of two numbers. Once we've got that, we have no more radical symbols and we can solve as we would have in Algebra 1. And, whoops, sorry about that. So you should have been able to follow this and end up with x is equal to 1. Practice this question just to make sure that you are able to do this correctly. And of course, then we're going to check. When we check, we plug back in, we make sure we end up with a true equation, and then we know our solution of x is equal to 1 is correct. We have another example in our notes. Practice that one on your own, and your answer, the result that you should get when you solve, is x is equal to 2. So here is that part B all worked out. Hopefully you were able to come up with x is equal to 2 without any difficulty. And when we check, we can see that again, we end up with a true value, true equation, and so we know x is equal to 2 is correct. Now, sometimes when we raise both sides of an equation to an even power, a square, a fourth power, sixth power, etc., we can introduce extraneous solutions. And you'll see in the next example what that's going to look like. This is why it ends up being so important for us to check our solution and make sure that we end up with something that is true, a true statement. So what I'd like you to do now for example 3, you have a little bit of the strategy under your belt. Go ahead and pause the video. Know that you are going to use the same strategy, that you're going to square both sides of what's on the equal sign. Our radical symbol's already isolated on the left. The only thing that you need to remember is when you have addition or subtraction, as in the right-hand side here, 5 minus x, when you square that side, you need to FOIL. So don't forget that. You're going to end up with two different solutions. Check both of the solutions and make sure that they work, and then turn the video back on when you're ready to check your answer. Okay, so here you see all the steps worked out. You should have ended up with two solutions, x is equal to 8 or x is equal to -1. Of course, the next step is to check those solutions. What we find when we plug in 8 is that we end up with a statement or a sentence or an equation, 3 is equal to -3. And of course, that is not true. They're not the same thing. So we know we're going to need to reject the extraneous solution, x is equal to 8. X is equal to -1, however, passes our check with flying colors, so we know that that is the correct solution to the question on example 3. Just as a reminder, we're not always going to end up with an extraneous solution just because we have two solutions. Sometimes it's going to work, so that's why we need to check. Don't make an assumption, check. Now, when you raise a power to a power, you multiply the exponents. And this is something, again, you've been doing since Algebra 1. Here's a perfect example of it. And we know that the 1/2 power means we're really finding the square root of x plus 12. But when we square that, the 1/2 times 2 ends up being equal to 1. So it's as if they cancel out because their product is 1. Let's take a look at example 4, where we're solving equations with rational exponents. And this is not different than having the radical, but it does look different. So you can see we're taking the cube root on the left-hand side. So what's our strategy? Our variable, or our radical is, it's not radical, but our binomial with a rational exponent is already isolated. So we are free to cube both sides. So you can pause the video now and work this one out. You can turn the video back on when you're ready to check your answer. After cubing both sides, we solve as we did in Algebra 1, and we end up with an answer of x is equal to 4. So if you had a question on this example or any of the others, remember to write your question down on a post-it and ask about it in class. In example 4B, we're going to approach it similarly as to the others. And so what you're going to do is come up with a strategy and then carry that strategy through. In this case, because we're raising 4x plus 8 to the 1/2 power, that means we're really square rooting it. So we are going to need to raise both sides to the 2nd power and get rid of the rational exponent in that way. Turn the video back on when you are ready to check your answer to example 4B. So we got two different values and we need to check both of them, x equals 2 and x equals -1, and see if one or both or neither give us a true result and a true equation. So we're going to plug those in and turn the video back on when you're ready to check and see what the final solution is to this question. So if you plug them in correctly, you ended up with the solution x is equal to 2 working, and it came up with a true equation, but the x is equal to -1 did not. So we need to reject that as an extraneous solution. We know where there are equations, there are going to be inequalities. In this case, we have radical inequalities. So that's just where we see a variable underneath a radical, but it's an inequality, in an inequality. So we're going to solve these algebraically, and we have a real world application. Oh, actually, before we do that, we have another example we're going to take a look at. So here we're going to solve this algebraically in method 2. So let me skip ahead to method 2. And just like we did before, we are going to solve for x. In this case, that means we're going to isolate the radical symbol and then square both sides or raise to whatever power we need to get rid of the radical. But then once we get all of that done, we're going to have an additional consideration. So as we solve, we ended up with x has to be less than or equal to 21. But in addition to that, we know that what's underneath the radical, what we started out with is the square root of 2x minus 6. That has to be positive. It cannot be, or 0. It can be 0 as the smallest number, because we can take the square root of 0 and end up with 0. But if we try to take the square root of a negative number, we're going to end up with an imaginary. We're only interested in real solutions in this chapter. So that what that means is the square root of 2x minus 6 needs to be 0, equal to 0, or greater. So we're going to set that up as taking that radicand and saying it needs to be greater than or equal to 0. We're going to again solve for x. And when we come up with the final solution, it's got to meet both conditions. X has to be less than or equal to 21, and x has to be greater than or equal to 3. And that's how we're going to write our solution set. It's going to be all values of x such that x is between 3 and 21 inclusive. Last of all, we have a real-world application that we're going to take a look at. The time t in seconds that it takes a car to travel a quarter mile when starting from a full stop can be estimated by using this formula. And we can see that it depends on the cube root of W over P, where W is the weight of the car in pounds and P is the power delivered by the engine in horsepower. If the quarter mile time for a 3,590 pound car is 13.4 seconds, how much power does its engine deliver? Round to the nearest horsepower. We're going to start this off by taking our function and the function that's been given to us, and we can either solve for P directly, leaving the variables in for T and W, or we can plug in. And in the PowerPoint here, we're showing plugging in the values that are given to us in the question first, and then solving for P. Once again, we can do it either way, solve for P first or not. But as we solve, you can see that we end up with about 295 horsepower when we round to the nearest horsepower. That does it for section 5.8. We'll hopefully be able to answer all of your questions in class and in our test review and take our chapter 5B test.